In May 1958, General Electric made its first industry-wide announcement of a turbofan engine on test. It was the result of a number of years of research, going back as far as 1953. In 1955, a GE front fan engine called the D2 was evaluated at Evendale. Turbofan blading was attached to the front of the compressor rotor. The extremely high tip speeds necessary on the D2 front fan and the vibration characteristics of the long blading raised problems which limited the practicality of this design. After several test runs, the front fan program was stopped. Although development difficulties were encountered, GE continued the investigation of mechanical design principles that would result in the cycle benefits inherent in the bypass design. Of all the bypass engines studied, the aft fan design offered the most benefits. Since the fan could be attached to any gas generator, it allowed independent development of the turbofan and the engine. As it was not mechanically connected to the basic engine, it had no effect on the acceleration rates or starting loads. Attached to the developed CJ805 engine, it produces a 35 to 40% improvement in takeoff thrust, a 20 to 40% gain in climb thrust, and up to 18% more cruise thrust. The aft fan design allows the bypass compressor to run at a different speed than the gas generator compressor, both units traveling at their most desirable tip speed. The major component of the aft fan, called the bucket, combines turbine bucket and fan blade in one stage. Engine test results prove that the mating has been a successful one. For these improvements, there is no increase in fuel flow for a given power setting. From the first tentative experiment, General Electric has expanded to an extensive program for bringing aft fan benefits to transport purchasers. One evidence of the soundness of aft fan design was its rapid, almost trouble-free development. From initial design to the first run was only 6 months, and a 150-hour test was successfully completed only 4 months after that. Highest time on any one of the 8 aft fan engines on test was 369 hours as of May 1959. The aft fan design required no mechanical or thermodynamic changes to the basic engine. In a vertical assembly, the pre-assembled fan package is moved into place and lowered onto the engine in half the cycle build-up time. It's also possible to attach the fan package horizontally. Aligned with guide pins bolted in place, the aft fan unit is ready for final assembly. Pre-aligned bushings slide down over the pins, allowing a precision fit in minutes. Essentially, 3 changes to the basic CJ805 engine converted into the fan version. First, the rear turbine frame is removed and replaced by the fan front frame, along with the rest of the fan package. A heavier oil pump is added, plus a slightly different main engine mount on the compressor rear flange. Design, of course, is only as good as actual engine performance. The CJ805-23 engine, being monitored in a test cell, left this record of its performance. Revving the engine up from idle to full power. This time it takes 5 6/10 seconds. From approach, or 20% power, to full takeoff power takes 2.5 seconds. The recorder makes a permanent trace of parameters. A closer look at the recordings shows exactly what takes place within the engine. Basic engine speed in revolutions per minute. Fan revolutions per minute. Throttle movement. Angle of movement of variable stator vanes from closed to open. Exhaust gas temperature as measured in the engine nozzle. And pressure in pounds per square inch measured in the compressor exit. Throttle movement is initiated from idle position to full takeoff power. 5 6/10 seconds after throttle movement, the engine reaches full takeoff power. Basic engine rotor and aft fan stabilize at exactly the same time, without hunting or surging. The variable stators open during acceleration at the intermediate RPMs and remain in the open position until the throttle is retarded to idle. The compressor discharge pressure curve shows a typical CJ805 increase pattern with no erratic pressure fluctuations. If an aircraft should miss its landing approach, full engine power is needed quickly. These tracings show what happens when the engine is running at approach, or 20% power, and full power is demanded. Temperature and pressure respond without delay, and in 2.6 seconds, the engine is up to full power. This bogey involves moving the throttle suddenly from full power to idle, holding it there until engine speed approaches idle, then rapidly re-advancing it to full. As this tracing shows, such violent throttle movement can be accomplished without any erratic responses from the engine. During early 1959's below freezing weather, a series of anti-icing tests was conducted at Schenectady, New York. No engine operational difficulties were encountered on the aft fan engine, either as a result of ice accumulation or other causes. At temperatures down to plus 22 degrees Fahrenheit, ice occurred only in very small amounts, even at liquid water contents of 4 grams of water per cubic meter of air. Another outdoor test activity was Phase 1 testing of the CJ805-23 thrust reverser. The test was completed at one of 3 sites at General Electric's outdoor test facility in a forest area near Peebles, Ohio. Using a standard CJ805-23 engine with a test rig reverser, engineers fully demonstrated the performance capabilities of this thrust reverser design. During operation, the fan rotor was instrumented with strain gauges to detect adverse effects induced by the reverser. The test was successfully completed with positive results. Thanks to tests such as these, fan reversers are receiving final design approval before hardware is installed in the Convair 600. Although fan engine pod configuration is still being improved, it will look basically like present designs. With the access door open, the whole gas generator will be open for inspection and in the pod maintenance. One of the most outstanding recent examples of CJ805 reliability is the flight testing of number 1 and number 3 880s. Together, they have totaled 500 engine hours by May 1959. Their trouble-free engine flight experience has furnished a successful operational record of CJ805 single-rotor, variable stator design, the basic gas generator of the aft fan engine.